Hi, everyone. Thank you for coming. I think, I don't know about you, but I starting to feel that we have actually community, right? It's like the vibes outside now, super. So I like all the discussions, and it's not about free beer, it's about something technical, which is also cool. So thank you so much for coming, because I see that a lot of people, it's not the first meetup that you visiting. So thank you for that, because we trying to build a community here, and we try to be the community. And thank you, Pascal, because this is, I think you're the first local who actually reached out and said, "Oh, okay, I want to prepare a talk." Thank you so much. I mean, since we started that in Google, of course. I just wanted to, some technical stuff, that we still use meetup.com for registrations and for preparing these badges. And for some of you, we needed to print them manually, and it kind of stops us. So if you please can do two things. If you have just your first or your last name in the meetup.com, can you please set both of them? It's not necessarily your actual name. You can put null. I don't care. This is the first thing. And the second, please try to register couple days in advance, maybe 3 days in advance. I'm okay registering, but still it's kind of, a bit tiresome. Okay, thank you so much for coming. Today we have just one talk. Next month will be another meetup, also here. We will have 2 talks from visiting speakers, and both of them are members of the standard committee. So you can bring your tomatoes and throw. That's completely fine with me. I think they also will be fine, but one of them is really huge, so he can kick you back. Okay, enjoy. Thank you so much for coming. Please, Pascal, the stand is yours.
All right, thank you, Sergey, and welcome everybody to improving safety and security using static analysis. We're going to be, let me just double check whether everything works. All right, there we go. All right, so who am I except somebody with computer problems? My name is Pascal. My background is in static analysis, mostly spent in the systems verification group at the University of Oxford. I was part of that group about 10 years ago, with a bit of a focus on not just static analysis, but also program synthesis. And my open source contributions sort of fall in that field as well. I was a contributor to the CProver suite, which is model checkers like CBMC and JBMC, includes abstract interpreters like Mariana Trench, which are more on the Java side. I'll try to use the J word carefully in this group. But of course, there's a bit of an overlap with these tools between the 2 languages. And full disclosure, I gave a talk about a month ago in the same vein about Java as well. So if I ever do slip up, feel free to throw those tomatoes that apparently you're hogging and preparing at me as well. But I'll do my best. So for today's agenda, I just want to briefly talk about sort of the background, challenges that we experience in software testing, why that might not always be enough. Give a bit of an introduction to static analysis, and then go through the different techniques one by one, sort of from lower to higher precision. We'll talk about that in just a bit more. And then I have 2 demos, Infer as an example of abstract interpretation, and CBMC and ESBMC. I'll talk about the split in just a bit, to which I contributed a bit more and will be focusing on a bit more. My goals for today is that just all of you, when you walk out of here, you have some idea of what kind of static analysis tools are out there, sort of on which spectrum do they exist, what are their strengths and weaknesses, where could they be used. So if you find yourself perhaps in a security situation where you're wondering, how could I check this for intrusions, or how could I protect my program against injection attacks, you might have some idea what kind of tools would be useful there. But, and full transparency, also know the trade-offs of these tools, and there are many. And also full disclosure, just because there are that many trade-offs with these tools, I hope some of you, all of you are probably C++ developers, will consider actually contributing to these projects. For many of these tools, using them usually means contributing to them just because they lack functionality, not in their core, but sometimes just, they might be they might not support the most recent C++ versions, for instance, and these kind of things. They frequently are lacking in that regard for silly reasons. And my hope today is to motivate some of you to eliminate those reasons and move these tools along as well. All right. So I guess just sort of a primer. Usually we can probably skip over this slide, but I assume most people sort of are aware that testing and software quality is important, and that where it's lacking, it can lead to disastrous consequences. The usual examples, and that's a bit of a drawback in my field. If you work in static analysis, you get a bit of a sense of appreciating disasters because they usually justify research grants, etc. But a few of these are also interesting examples. Like for instance, Knight Capital Group, I think, had a trading glitch where they lost millions of dollars in seconds. Did they finally go bankrupt? I see. I thought when I read up about it, the joke was that they didn't go bankrupt, but I guess eventually it got to them. But yeah, that's sort of the reason why I bring up these examples is because apart from the usual testing that we do, sometimes we can actually think about fairly straightforward invariants, perhaps, so like some properties that should be true about our software, like with Knight Capital. Well, we shouldn't be losing massive amounts of money in a short period of time. That should be impossible if we write our program correctly. And that's exactly like what I'm trying to further here, sort of this kind of thinking about not just about tests and test inputs, but hopefully also about properties in your programs. So, quick disclaimer, I'll be talking about a couple of static analysis domains, and I might be using these terms here. So first of all, when we talk about static analysis, what I mean by that is it's a fairly trivial definition. It's usually just about analyzing a program without actually executing it. That would then be dynamic analysis. The benefit of this usually is that it's not limited by runtime constraints. If your program takes a long time to run, your analyzer is technically not bound by that. But hopefully also you can just explore what the program does in a much more global fashion than just using specific inputs. I will be talking about precision a lot because that's the trade-off that you usually have to take with static analysis. I'll briefly start with linters. I assume everybody's familiar, just to sort of as a starting point, and then we'll go into AppSec interpretation and what I would call full-blown model checkers. I will be referring to, syntax of programs versus their semantics. Again, obviously linters are usually driven by syntax. By semantics, I usually mean the behavior of the program or the meaning of the program rather than just what it looks like and how it is expressed in a particular language. I might be mentioning approximations over and under approximations. That usually just means that when you have to be imprecise, are you effectively on the false positive or false negative side, and I'll try to stick to those terms just because I think most people are familiar with those. But that just means usually when you model the possible state that these programs can be in, an over-approximation for your intuition would mean you assume that more states are possible than actually are because it makes it easier for you to traverse that state space if you have that assumption. And that would usually be the case in like a safety scenario where you want to be absolutely sure, and if your over-approximation is safe, then the program is definitely safe as well. And under approximation scenarios will be where we actually model less of the program, so we might have false negatives. But this is either necessary because of performance or because we don't care about it that much. For instance, one case would be security analysis, where we're just trying to find injection bugs. And so long as you find these traces, it doesn't really matter that you find all of them, you're just trying to effectively find a number of them. In the same vein, soundness and completeness, completeness would mean that depending whether you're like in program analysis or program synthesis, but soundness would mean that every program that is marked as safe is actually safe. And completeness would be that you actually only mark faulty programs as buggy. So this is again like a false positive, false negative situation. I'll try to stay clear of the terms, but just in case they pop up, I hope people have an understanding, just sort of to try and place these. All right, so what are you going to look at today? We'll start with, from top to bottom, the technique that most people will be familiar with. Linting is sort of a pattern matching over the program's abstract syntax tree. And by the way, I agree with Sergey that if anyone has any questions or wants to dig in somewhere deeper, just shout. There's a cube that can be hand it around. Yeah, sorry.
So you're mentioning precision, but kind of what do you mean in this case? Is it just how accurately you can get to the source of the issue, or is it just more something else?
It's effectively you can imagine it as a false negative or false positive rate. And the lower that rate, the higher your precision. But thanks, yeah, I should add that to the first slide. All right, I don't think we'll be needing the cube. I can hear the cube. I can hear it just fine. So obviously, most of you are familiar with linting, and what you can catch with that is usually bad practice or common errors that can be sort of derived from the syntax of the program directly. Precision in this case would be fairly low, as you all probably can imagine. You'll be missing cases like that if it's not expressed exactly in this fashion. The same program can be written in many different ways, but it's fast. You can run it before your Git commits, and it will work. It will show you some errors. If we move in the direction of model checking, we're talking for all of these tools that we have some possible state space of these programs that we try to explore in one fashion or another, and hopefully in an efficient fashion. Usually, these are much more general purpose. So with these tools, you can actually express any property. You could, for instance, say that we'll see later an example that whatever my trading engine does, profit should never be negative, and the tool can verify that that will be the case. Usually, that means precision is very high, but unless we do something, performance will be extremely slow, and we'll get to why that is the case. When I say doing something about performance, we immediately go into abstract interpretation. That's where we sort of decide that we're not exploring the program in its actual form, but rather some abstraction of it. That might, for instance, mean that we only track certain properties, say a null pointer check. So we're only interested in are variables null or are they not null. We don't care what their actual precise value is, and that already helps us to make some decisions about the program. This is usually done for specific use cases. So this might be injection or, again, nullness properties, etc. Their precision I would thus classify as medium, and they're faster, definitely as a classic model checker. But the domain that I've spent most of my time with would then be symbolic model checking, where we try to interpret the program precisely, but do so in an efficient representation so that we can check general purpose properties. Precision will be high, and I'm never quite sure what to put on the performance side. It's, as you'll see, it still takes obviously some quite heavy engine to still reason about these programs, but we're a long way from the model checking world where we're actually able to reason over real world programs in an efficient manner. All right. If there are no questions there, let's just get linting quickly out of the way. I think most of you are familiar with it. One example is CPP check. It's general purpose in the sense you can specify any rule that you want over this AST. But of course, it's limited by the number of rules people are willing to express. And these could be perfectly precise. These could cover every problem that you might ever have. Granted, if you use an infinite number of rules. They sometimes involve some data flow analysis, which pushes them a bit towards what I would call model checking. Sometimes they require user annotation support. But beyond that, I assume everybody has a bit of an intuition what linting is and what we're not talking about today. If we go into the model checking domain, there, again, just to differentiate between dynamic analysis, we would have testing, where you explore specific inputs. You have certain precise tests in mind that you want to work with. And an expansion of that some people might actually mistake for model checking would be fuzzing, where you try to explore many randomly generated inputs, hopefully even all possible inputs for your program. Usually these are guided in one fashion or another. So you might have like some semantic-driven fuzzing where it, for instance, tries to decide based on the types. If it's a string and it reads the context of the method, it might decide on certain strings that look like an SQL statement or things like that. It might bias its search towards that. But still, usually you're already struggling here with a state space explosion. If you have a method which accepts a string, which should be an SQL query, there's an infinite amount of queries, an infinite amount of character combinations. You're not going to explore all of those likely with just fuzzing. And that's precisely the goal where static analysis comes in. Usually we have some explicit representation of your program stage, and we would like actually to explore its behavior universally over every possible input. We perform this analysis over this intermediate representation, and we might apply some property-dependent optimizations just because the state space very quickly, of course, can explode. To give you an example of what that means, obviously, if we just take method foo as our entry point in this example. It's an integer, so it's already 2 to the power of 32 possible values that we would have to explore, 4 billion values if we were to use fuzzing. That's manageable, but it already would take some time. And you can imagine any real-world program is going to have config files, it's going to have user input. It will have a possible input space much, much larger than just this. And with fuzzing, we're very quickly going to reach the end of it, but using model checking, what we can do, for instance, is apply optimizations like pruning, like extractions. And the example here, we can, for instance, say, well, if foo is our entry point, and then we invoke the method bar, looking at the implementation, if we care about states rather than inputs, for every value of I that is less than 0, we will end up in the same state in foo. And so we can actually prune. We can say, well, there's no need to explore the other ones. We only explore the values that are actually going to be relevant. So we sort of immediately cut our possible state space in half. And this is one optimization that's precise, but of course others will be imprecise as well. Speaking of imprecision, one I'll say a popular optimization that we will talk about a bit more when we talk about our first actual analysis engine is abstracting. So what we can do actually is, instead of reasoning over the program in its actual concrete form, we have so-called abstract domains. An example of this, probably the simplest one, is the integer domain, where we decide, well, for integer I, we don't run this program for every possible integer. Instead, we try to analyze it, still step by step in program order, but we try to analyze it for every possible input at once. What does that mean? Well, instead of having an actual number on the input, in this case, what we say is we represent our integers as ranges, as intervals. And we say at the beginning, when it's still unconstrained, it will be, of course, from negative to the power of 32 up to positive to the power of 31. But then we interpret the program, and instead of executing the program, we so-called symbolically execute it and modify not the actual state of the program, but our abstraction of the state. That's, by the way, when you write the static analysis tool, usually you write some kind of compiler, you write some kind of front end, and then some interpreter that will still read the code, will still interpret instruction by instruction, but instead of, for instance, changing a variable in memory to a concrete value, you change your abstraction of the program, and hopefully at the end this will allow you to reason over some interesting properties. In this case, for instance, this means after this guard, after this I less than 10 or I greater than 1,000, we would return. What does that mean? Well, we can now restrict our domain. We now know that after this if statement, our value of I will be between 10 and 1,000. If we multiply I by 2, we know now it will be between 20 and 2,000. If we check that it's exactly 1,001, you get the picture, of course, it will be a range of exactly one number, and that is already very useful. But of course, this is an abstraction, as there are many. And so if we look at the else branch, what can we conclude there? If our domain is just an interval, a single interval, then we have no way of representing this additional information that we just gained. That means we stay with the original one. It's still an over-approximation in this point. So we're actually assuming that it could be anything between 20 and 2,000, even though that is no longer true. And that means this assertion here, we will not be able to verify that this one actually works. We will get a false positive here using an abstraction like this. Now, this is a fairly straightforward example. These domains can get quite complicated. You sometimes use either multiple intervals, or you use specific for your property. One domain, for instance, would be something null or not. So your domain is nullness. You don't care about the value, but only is it null, or does it have an actual value? And we'll see in the first section a bit of a practical example how this could actually be useful, right? I mean, in this example, of course, if your program is nothing but numbers, you could see why this might be useful, and you might be able to prove some useful properties about this. But most of us probably work with more general purpose C++ programs. But the main takeaways is, yes, we have the state space explosion problem, and the rest of the talk will be kind of about solving that. I assume if we didn't have this problem, if we could efficiently explore every single state, then yes, we could just execute the program. And if we hit an assertion and it's false, then we have found a bug. But for the rest of the talk, we talk about abstract implementation and symbolic execution, where we try to do that in a more efficient manner. And yeah, these abstractions usually have trade-offs. you have false positives and you have false negatives, which you might be fine with in safety analysis. If you prove your card to be safe, even with these false positives, and it's even in this over approximation, it's not possible to have a bug, then you're golden. And usually, the counterexample in security engineers usually are only interested in finding a certain number of issues, actual traces that they can use. We have an example from my background in a previous company I worked at, which was Lacework, where the usual rule was our abstraction tools would have a true positive rate of about 20%. That means if a security engineer looks at 5 traces, they will find one actual injection attack into their program, which for these domains is good enough. That helps these engineers actually. All right, the first example I want to mention here. Yeah.
Is this formal verification or like a subset of formal verification, or how do the two relate to each other?
Abstract interpretation versus.
Model checking. Yeah, I can use it. So is model checking a kind of formal verification or the other way around?
I think it's on.
Can you repeat the question?
Yeah. So the question was, is model checking a form of formal verification? And yes, I would describe formal verification as a superset, which includes things like abstract interpretation, which includes things like bounded model checking or model checking. All right. On Infer. So Infer is the first tool that we will see in action. It's a very feature-rich abstract interpreter that, as I said before, is usually intended for specific properties. So when you go on the Infer website, it will tell you there's these different backends. One is for nullness checks, one is for resource leaks, another one is for concurrency or for injection attacks. And in the C++ world, of course, mostly people are interested in properties like null pointer dereference, memory leaks. And as you can see, there's just another property where you, instead of keeping track of the entire program, you're just checking certain instructions, new instructions, delete instructions, do they occur in the same environment? The nullness one is probably the easiest example, but the one that I think is interesting for security is the injection attacks. And for your intuition, what that means in the nullness check, what you would, for instance, keep track of for this variable p. This is a pointer in this context, and it's a bit of a silly example. We'll see the full code afterwards, but basically you pass it to an increment method, and it will then dereference the pointer, increment it, etc., return the new pointer, or ultimately the same pointer, but it might return null. And this is a property that gets tracked by Infer. It sort of checks that at the beginning, p might be null, may or may not be null, but after this method, it may only be an actual real object, or it might only be null. And that's the only thing that Infer knows about and checks. And this also allows it frequently to have sort of summaries, where you can say that, for instance, you would have summaries over increment, where you could say, well, we don't want to have to analyze increment over and over again. We're going to analyze increment once, and for instance, we're going to check, does it dereference any of the arguments that are passed into it? If yes, then we just know passing something into increment is effectively dereference. So we don't care how exactly it happens. It's just a summary of it. At the same time, we also check what does it return. Can it return null? Can it return only valid objects? Does it return the same object that we pass in, etc.? These are like the summaries that you evolve over these programs. And that allows you to be more efficient about this. But of course, this only works if you have an abstraction, because if you have the concrete state, summaries of that eventually become your whole program state again. And I want to briefly show this with a video, which hopefully will not be getting stuck on me. So this is the infer null pointer analysis as it works out of the box. As you see, this was the method that I was discussing before. Fairly, oh wait, that doesn't look right. I think I'll need to exit out of the slideshow. And yes, I think we're extending for some reason. I would prefer to duplicate, but I won't be tempting fate here, so we're doing it this way. So yeah, this is the method I discussed before. Fairly straightforward, accepts an int pointer if it's implemented correctly. If the pointer is null, it returns a null pointer, otherwise it increments it. And if we now continue, We have our harness, which we assume is our entry point. So we don't restrict the inputs here. So we actually assume that P could be any type of pointer. That means it could be null and some additional condition that we talk about later. And as you can see, if I run infer on this, it already says from the previous one, no issues found, but let's just show that this is a real tool that actually works and can be executed. Usually always need to specify the build tool as well. It copies, it detects which files exist from the build tool. And you see no issues found, which makes sense. So as you can see here, the state, for instance, of the pointer P is transitioned into the is not null parameter. So, you know, this stuff works as well. It then actually has a guard and checks it. And it knows, yes, we're dereferencing P in there and P might be null, but infer is aware, of course, that this is unreachable and that this doesn't work because it's directly linked to the variable P and the state, or rather the abstraction of it, null or not null, is passed on into the is not null variable. However, and there are, of course, cases where this does not work because infer is only interested in nullness or not null. So its abstraction, for instance, doesn't cover this. This is an example which would actually be unreachable as well. You know, a number cannot be both even and odd at the same time. So this branch is unreachable. Silly example, perhaps, but obviously this would be actually safe. And there might be many other situations you can imagine where, based on the concrete state of the program, based on other variables, a program would be safe. And actually, this would be false positive to report. But of course, infer only looking at nullness of pointers, etc., will not be able to decide this. It will not look at other variables, and hence you will have issues like these. Now, this depends again on what concrete backend you're actually using with infer. There's, if you go on their website, there's a plethora of them. And I personally, for the scope of this, probably the most interesting one, in my opinion, is the injection abstraction, where effectively infer will do exactly that. It will just have a measure of, well, is this input that is coming into my method, say my REST method, user controlled? Is it something that a user can pick and could perhaps introduce escape sequences into? Does it, one way or another, through other variables, through fields, however it's passed through, reach, for instance, an SQL API, which would be a vulnerable sink? For these kind of approaches, it works extremely well. We've used it at my previous company, Lacework, as well. And as I said before, for security engineers, this is a fairly interesting property to assure. And it's also, if you're developing your programs in a somewhat reasonable manner, it's also not, even though it is, of course, an over-abstraction in that sense, it's actually easy to write your program such this will never be an issue with infer. Or rather, infer will not give you false positives and your program will be marked as safe. Now, any questions on these abstractions? Otherwise, we're going to go into the symbolic execution portion. Mm-hmm. That's correct, yeah. It's actually even, oh yeah, sorry. The question was, is this tool independent of the toolchain or the compiler? The answer is yes. Infer has its own intermediate representation. It's used for C++, Java, and Microsoft, I think, created even Infer Sharp, which is a C# front end, mapping .NET IR to the Infer IR. But I think the most used backends are C++ and Java. All right, now let's see if we can switch back. Well, we can, but I should have. Let's move. Oh, there we go, just the right slide. All right. So moving on to which might be perhaps for C++ code interested in safety, perhaps sort of the more impactful tool. This is one that I contributed most to, which is CBMC, stands for C Bounded Model Checker, but it has a C++ frontend as well. With this tool, mostly intended again at safety checking, you can actually have your custom assertions. So you can put an assertion or other properties in your program directly. We'll see what that looks like in a minute. And it has default implementation for common errors like uncaught exceptions, null pointer reference. It will report those. But it will also allow you to specify your own assertions. Say, for instance, in your power plant, the temperature should never be above a certain value, never be below a certain value. These are kind of like the properties, that these abstract ideas that you can express over your program in order to sort of prove them safe under all possible inputs. And we'll see that later. That's really the nice part about this. If you actually go through the effort of using this tool and analyze your programs with them, it will be, you get the nice, safe feeling that there's no possible input under which your program will ever end up in this undesirable state. That means to get there, of course, as I said before, in order to explore all these possible states precisely and efficiently, what we do in CBMC is that we map it to effectively a formula, an SAT or SMT formula, which is satisfiable if and only if your program has a bug or your assertion can be violated using a certain input. And the concrete assignment that it finds is actually what will give you the trace, proving exactly step by step how you end up in this undesirable state. For those of you curious, I'm not going to spend too much time on this, but in my last talk, people asked that they could please get some intuition of how can you actually map a program to a SAT formula. What does that even mean? First of all, it's always bounded. That means either we specify invariance, loop invariance, to be able to reason over the body of a loop exactly once, or we unwind it, meaning we say we're only interested in inputs that unwind this loop 10,000 times, 100,000 times, and any list that is larger than that is going to probably behave the same way as anything else, so we'll be fine there. We do some transformations on the program, things like single static assignment, which again means that you keep track of every value that your variable has ever had and express that in independent variables. And what you see here is an example of bit blasting. You see on the left-hand side, for instance, we set the value of foo to 7 initially. But what does it mean? Foo is an uint 8, so it has 8 bits. And so we effectively create 8 variables in our SAT solver, where the first 3 are true and the other ones are false, modeling the binary value of your variable. We do the same for bar, where we set it to 10. So as you can see again, the negation. Is everybody okay with the syntax used here, by the way? With the conjunction and the negation? Okay. Yeah, okay, apologies. So this would just be, usually this would be in, of course, in disjunctive normal form or conjunctive normal form, but this is a conjunction, meaning these variables have to be true, both for the formula to be true. This is a negation, so variable foo 3 is expected to be false. And here I'm just keeping track effectively of which value it was. So this subscript 0 means it's the 0th or the first value of foo, and the superscript is just which bit it is. And these are all independent variables that you could have in a SAT solver that will then give you a satisfying assignment for this. So you could, for instance, choose for this value true or false. And of course, if you make all of these true, then the formula becomes satisfiable. And but if, for instance, if for this part of the formula, if foo03 were true, then this formula would be not satisfiable, or not satisfied rather. And yeah, so this, what it effectively means is this is 0, 0, 0, 1, 1, 1, and then 0, 0, 0, 0. And here we have 0, 1, 0, 1, etc., modeling the binary value of 10 effectively. And when we, for instance, do something like this, where we assign foo to bar, what we effectively say is that the new value of bar, subscript 1, should be the same as foo, but we don't restrict what foo would be, right? Or we want it to be the same as foo 0. And that kind of means we say, well, this 7th bit of bar needs to be true if the 7th bit of foo is true as well, or they both need to be false. Again, just a way of expressing equality in a SAT solver. Again, this is details that I promise you will not have to know when working with CBMC, but I just want to give people a bit of an intuition of how these tools work so they can talk about it when they decide to use one of these tools, or if you're in a, say for instance, in a sales discussion with somebody from Coverity, that you have some intuition about, okay, what are these tools, how do they work, just to pull back the curtain a little bit. Does that sort of this intuition again with the SAT formulas or the SMT formulas make sense so far? Any further questions?
What's the speed as a function of length of code?
So worse, the question was, what is the performance of this technique specifically? That's when it as a function of the size of the code. Excellent question, because we're solving SAT formulas. They are worst case, of course, exponential. So it's an NP complete problem. We have to solve 3 SAT here. That was actually going to be my next slide. And what does that mean? It's worst case exponential in the size of the program that includes the loops which have been unwound. Now, the good news is that's usually not the case, because if you, just to explain how SAT solvers usually work, it's usually an algorithm called conflict-driven clause learning. That means if, for instance, a certain variable prohibits other variables to be true, then the SAT solver can actually work with that very well. And that, for instance, if you imagine on a program, that usually works out quite nicely, because you have, for instance, a guard that's false, and that means everything else in that if body is unreachable, and so the conflict-driven clause learning goes all the way through. Like, all these variables can be immediately decided whether true or false. But what you can also do with CVMC, and we'll see a bit of that in the demo, you can try to solve cryptographic problems. You can tell CVMC, well, here's my input is a key that I don't define, and here is the whatever, like AES encryption algorithm, and here's the encrypted text. Give me a key that will, using the SAT solver, find a key that will actually decrypt this message for me. And you can absolutely do that. CVMC will find a solution for you eventually. But in cryptography, these kind of problems, that's exactly where the exponential time is going to hit you. CVMC, there's absolutely no correlation between the bits. It's meant to be completely random. And so CVMC will effectively have to explore a lot of combinations using that SAT solver before it finds that key for you. But luckily, most of our programs, I should hope, are not completely random, but have some logic and some coherence to them. And that's actually the surprising thing, that a lot of time these tools can actually solve those formulas in polynomial time. So it's not unheard of to have millions of variables and formulas in the clauses and formulas in clauses and variables, now we got it right, in those formulas. And they're still being solved within minutes. So it's usually, it is a correct assumption that larger formulas and larger programs will, on average, probably produce longer runtimes. But again, not always. Sometimes if a bug is completely obvious and trivial, this will be found very quickly if these implications immediately trigger the conflict-driven clause learning. All right, now to the nice part of this. What does that mean? I wanted to show what can CVMC actually do. And I think today, other than in my Java version, I think we actually have the time to go through that, because usually what I'm going to do is I'll show you the usual examples just to give you a bit of an idea of how powerful, I guess, this can be. They're the usual examples that people in my field will always give in all of these talks, and they might be a bit trite, but I think I have a contractual obligation to bring them. And then we talk about something more concrete, about an actual real-world program-ish, one that I came up with for this talk, and see sort of whether we can find bugs and whether CVMC can actually help us find those bugs for us. So the first example is the cryptographic example that I mentioned before. I just took an off-the-shelf hash implementation, Murmur 3, from Wikipedia. I hope I'm not violating some copyright by doing this, but I'm sure it'll be fine. And as we can see, I tried some input for CVMC, where I tell it, well, this is my method, non-deterministic input that I want to use a couple times. We'll see later. And as you see with CVMC, you can specify these additional assumptions as well, where you can say, well, this input should be in this range. Anything else I don't care about for the scope of this analysis, whatever that might mean. And of course, you have to be careful with that, because what you assume to be the correct range might actually not be the case, right? You're actually excluding like an actual attack or a safety critical input using the assumptions like these. But CVMC has a lot of tools like these for you to create them. And what I'm doing here is I'm telling CVMC, give me a character array of 5 characters, and I'm giving it a safety assertion. I tell it, my program has a bug if the hash of whatever you come up with has the same value as the hash of hello. That means I'm effectively challenging it to find something that has the same hash as something that I already know, as like a password. Give me another sequence of characters that has the same hash as HELLO, which would be a hash conflict, right? So you're tasking CVMC to find a conflict in this algorithm. And of course, CVMC will dutifully comply. I'm going to, well, past me is going to run the script. And yeah, in the output here, we can see this is what a usual trace from CVMC looks like. So it tells you that it solved this variable or this formula. So the SAT checker found actually a satisfiable instance. That means there is a bug. It will give you kind of like a debugger, step by step, which assignments it went through to do that. And there's also something you might also like a debugger that sometimes means you have to sort of perhaps introduce intermediate variables or something like that if something that's actually interesting for you. But as we see here, the sequence it came up with was underscore, closing bracket, some non-printable character 5 in ASCII. I forgot what it was, probably some ETX or something, Q and H. And if we now check by just executing the program with this input, a bit further below, as we see here, I'm just creating a new string with precisely this input that CVMC provided me. If I execute this now, it should be exactly the same hash as the hello. Yeah, which is nice. Again, sort of these problems, it's just a good example, usual hash function, you're giving CVMC the goal, and it just tries to find any assignment that will satisfy this goal, even a hash function that is usually meant to be not invertible. All right, and the next obligatory example that everyone gives is, of course, well, we can use this to solve Sudoku, if we're particularly lazy about this. So what I have here is actually, I didn't implement any backtracking algorithm in this program. All I implemented was a function that allows me to check whether the input here is a valid Sudoku. At least I think I implemented that correctly. We'll see in a minute, but yeah. So that's just the code, returning true or false, whether something is a valid Sudoku. And I'm telling CVMC again, give me a number between 1 and 9. Here I can fairly safely assume that's the only number that would be useful. So I'm just making CVMC's life a bit easier. And now I have my Sudoku that I prepared here. And just for the sake of demo, I actually only removed 3 numbers, 7, 4, and 8. By a non-deterministic int. So that's an input. Those are 3 variables that CVMC gets to choose. In your program, this might be user variables that a user might input, and you're trying to prove safety for those variables. And now I'm telling CVMC, well, if the Sudoku is valid, then you found a bug. So I'm just asserting is not valid. And again, this is no problem for CVMC. We just run through it. And we should get, this is actually the last variable, but if we go to the beginning, we get 7, 4, and 8 as the outputs that CVMC chose in order to violate this assertion. So these are all just sort of, I guess, demonstrating what SAT solvers can do for you, what kind of formulas they can solve, but how does it actually work in like an actual testing environment where we have certain functionality that we want to test. And that's exactly where I want to emphasize it's okay and correct to think of our programs as tests and as fuzzing, trying to make them work with specific interface inputs. But we might also perhaps think about general properties that, again, companies like Knight Capital would have been interested in. For the purpose of this demo, what I have here is effectively a product database that, since we're in Switzerland, the buy price is in Rappen, actually. So we have a certain sell price, a certain buy price, we have a certain amount. And of course, the difference between what we buy them and what we sell them for would be our profit. I register 3 products in here, one with a fairly modest profit margin, 1,500 Rappen, I think, so like 15 Swiss francs, and we have 10,000 of them. The next one has a margin of 5,000, and the next one, actually, I think is the biggest one, which has 100,000 profit margin. Fair enough. And I implemented what I assume to be a fairly reasonable method for doing this. So we have a buy method where a user can indicate an amount that they would like to buy and a product ID. So they specify I want to buy X of product Y. Now, I think I already added a reasonable condition there. If the product ID is, of course, outside of the valid range for this array, we're not doing anything, we're just returning. But beyond that, I'm getting the product from my database. I am reducing the amount by what the user wants. I calculate the profit that I will be getting for each of these sales. I am updating the product with the new value, and I'm adding the amount times the profit to my variable where I keep track of the profit that I'm making. This sounds fairly straightforward. It's a small method, a small functionality. What could possibly go wrong? Don't pay attention to those line 28, 33, and 39 where certain things are hidden from you. Don't pay attention to the man behind the curtain, but there's just obviously a few additional conditions, as we'll see, that I need to add. But what I can do now is I can tell CBMC, well, instead of what we usually do, if we go to the, move more quickly, Pascal from the past. So what we see is usually like a test case as we usually would write them. Again, I have an input where I want to buy 10 items of product 0, and I expect a profit of 10 times 150. That's great. Or I buy one item of item 1, and I expect a profit of 2,000. That being added 500 on top of what we had before. Yes, of course, these tests make sense. We all of them write them. But what you will be doing in CVMC, and what might be interesting, especially if in like a safety critical environment, is something like this, the next harness, where we want to say, well, for every possible amount that a user might be typing in on the website, for every possible product that we have in our database, and that's why these two are parameters, they're free variables as far as CBMC is concerned. For our shop, if somebody buys them, well, what are useful assertions, general properties that might be useful? Well, we should always be making a profit. That would be nice, right? We shouldn't be losing money. No matter what a user types in, we want to make sure that we're not losing money. A second one that I added is that we should never have a negative amount. For instance, we should never run out. Also a useful property. And that's exactly, if you start using these static analysis tools, you start to sort of think about properties of your program, safety properties, rather than just how it should behave for specific inputs. And I sometimes liken it to parameterized tests, where you do something similar, where you say, I want to have a certain behavior, and I have a list of parameters, and it should behave that way for all of these parameters. Well, here we do the same thing, but all of these parameters is literally every possible input, which is what makes these safety checkers at the end of the day. So if we move on, does anybody think our implementation will be safe, or will it have bugs? Has anyone already spotted some bug in here? Interesting, yeah. So let's just see what CVMC has to say about that. But negative amount, yeah, I wish I had used the uint, but this was migrated over from an inferior language, Java, and hence I'm using int. But so yeah, let's take a look at what CVMC comes up with. What is the first example that will tell us? We get an output again, and we see obviously it's not safe. The negative amount I think will be the next example. But if we go here, what we see is usually exactly like the kind of trace that CVMC works with. That I said before, this is very similar to when you work with a debugger. We see here, okay, our method is being called, and then the product is correctly selected. It's the one with, I think, 5,000 profit margin. And then we see the amount of the product is set to a negative value at the next step. That's unfortunate. That already violates one of our assertions. So I guess again, question, how can we prevent that? What is happening here? Why do we have a negative value all of a sudden for the remaining amount of our products? What was that? I didn't catch it. Did you say overflow? Well, actually, I mean, in this case, it's actually simpler. I mean, we didn't check, we checked that the product ID was in a valid range, but we didn't check the amount. So a user can ask for more amount than what we actually have in our database. So simple check like this. I change this and immediately rerun CVMC. And just a few seconds later, obviously for a small program like this, we should get another output. And we see now the problem has gone away. The next CVMC still finds an issue, but it's no longer the case that the amount is negative, right? Which is already good. So we're not running out of stock. But what is happening here now? The original amount was 200,000, and now it's close to 2 billion, I think. So I think this is what somebody else mentioned. This is a very unfortunate scenario. Some customer decided to input the negative amount, and as we'll see later on, why this was actually caught by us. We didn't have to actually specify the negative amounts. Yes, we specified it for the stock, but the user was actually free to enter this. Beyond that, our safety property was not as explicit. The reason why CVMC is catching this is, of course, because if somebody is allowed to add in a negative amount, that at the very end means that our profit will be negative. So somebody sold these things to us at a profit rather than the other way around, a situation we would like to avoid. And again, this is something that you only had the property they specified was extremely simple. We need to make profit. And then it catches situations like these where a user might specify a negative input to simulate selling things to you, etc. You might have heard of like these stories in the US. It's become very popular to have these machines, card machines that allow you to specify a tip immediately. And I think you these days have to specify one. And I think some clever users or customers then came up with the idea of just specifying a negative amount in there and reducing their bill. That's exactly something that CVMC could catch for you using just a simple, fairly straightforward assertion. Again, we always want to be making a profit, no matter what the input is. So if only those card machine manufacturers had used a tool like CVMC, they could have prevented this. All right, so that's the second item that we should check for is the amount negative, right? Another additional check, straightforward. So we should be good now. Or not. CVMC is still giving us an issue. We still get a negative profit for some reason, even though we know people can no longer sell things to us. So what is happening instead? Let's scroll up in the trace. And this seems fairly reasonable. We had 200,000 of these items. After the transaction, we have about 6,500 left. So somebody got some 190,000 odd items. Yet we are still getting a bug, right? So we're going to scroll down a bit. We keep going in the trace to see, again, this is similar to how we would be using a debugger. And by the way, there is even like an Eclipse plugin that reads these traces and lets you scroll through them as if they were in a debugger. But yeah, so everything looks reasonable. But then by the end of it, we get a negative amount. And now, cue Sergey, what is the issue here? Overflow, exactly. Another issue that's caught. So of course, if I now go ahead and fix this bug in my shop, which should be the last item here. If I just apply a maximum value here that will not overflow, fairly straightforward to fix. But now I rerun CVMC again. And now probably for the first time in this rather pessimistic talk, we get a verification successful. And this is a nice feeling to have. I mean, this kind of means that for every possible input, any integer that can be expressed in the C++ language, the profit will always be positive. There's no glitch possible in this system where we would be losing money. We might be making not enough money. We might be making outrageous amounts of money. We might be scamming our customers, etc., whatever. But there's no loss ever possible using any possible input. And the same, of course, also we're never going to be running out of stock, etc. All these kinds of properties. You're able to verify using these. And yes, of course, this might not always make sense. Not all of your applications are going to be critical. But if they are, then these are the kind of techniques that might actually save you a Friday night emergency, whatever, a CEF call with your employer. So if we go back to the slides, unless there's any questions on these examples, on the code, on how to invoke CVMC. Mm-hmm.
One.
Yeah. Wow. Fascinating. So what's the case with real projects when you have various includes, dependencies, whatsoever, those all contribute to the final result? So how can you set up these methodologies with such complex interactions? Does the tool have an understanding of a project structure, or that needs to get filled manually, or how does that work?
Mm-hmm. Okay, so for once I don't have to repeat the question, so thank you. Yes, it does. So CVMC, we've seen this before with Infer, where it sort of acted a little bit like a build tool, like CMake or whatever. CVMC behaves like the most popular suites on Windows and Linux. So it has like GCC properties. You can specify -i, for instance, to specify an include folder, and it will find them for you. And on Windows, it behaves like CL, like the Visual Studio compiler with the same parameters. And yeah, you would specify, of course, your entire context, your entire program. You give CVMC an entry point, This might be your main function. It might not be your main function. It might be a REST API entry point, etc., that you're working with. But you give it the full context. And other than the Java version, it actually works on the source code because that makes it a bit easier if it still has the full context. CVMC has many frontends. It also has, for instance, a Java bytecode frontend. So for Java, we usually work on bytecode. It also has like an assembly frontend, so you can definitely work with that. But the analysis just becomes much more understandable if you work on the source code. Similar to, with a debugger, you want to have the symbols available, etc. And that's why it has this capability. So to answer your question, you would give it your entire project as if you were compiling it, and then it will perform the analysis and create a representation of the entire program.
Okay. So is there any chance that CMake can generate me these comments for verification based on the already existing CMake project description?
Yes, well, it's probably easier with the make file. Something like infer has direct support for CMake. For CVMC, as far as I'm aware, unfortunately not, no. So you will have to somehow grab that out of your files, whatever. Or, I mean, what you can do is specify star-cpp, etc. But yes, that is definitely a bit of effort that needs to be done to explicitly integrate it into your CI or build system.
Thank you.
Absolutely, yes. That's exactly where we're going with this talk, actually.
You mentioned it's working with the source code directly. So what happens if the compiler is optimizing something that does that ever have an effect on what's actually happening behind the scenes, or kind of how does that get dealt with?
Yeah, so it does work on the source code. Yes, you're correct, even though it has an assembly frontend that you could use in some scenarios. But in this case, what CVMC will report by default also are some specific undefined behaviors. And so the idea is that if your program is correct according to the C++ standard, then CVMC acts sort of as its own compiler, right? So you're using two different compilers. And that means if your other compiler, of course, is working correctly and your program has defined behavior according to the standard, then that is the assumption that CVMC makes you would be fine. If your compiler has a bug and it optimizes something that is no longer the correct program, that does not represent the original semantics, and it would not be correct according to C or C++ standard, then you have a problem, yes. CVMC would be missing that. It assumes that your compiler does not have bugs like that. All right, any more questions before we conclude? Yeah? Mm-hmm.
Hello? Okay. You mentioned that it has a assembly frontend. Does that mean that it works also with stuff like inline assembly or intrinsics? And also, like, what support can you expect? Can you expect like newer instructions like SSE and AVX to work?
The answer for that is, as I was last working on that, no, unfortunately, because they're two separate frontends. So either you have like a compiled binary that you add into it. You can combine them, so you can have like a compiled binary, and then you can add like C files to it, etc., and it will just create one model for it. We use that, for instance, for JNI analysis, where you have like part of the Java program, part of the C program, and you analyze them together. But for the example that you gave, you would have to effectively come up with a model for that, right? So CVMC allows you to specify your custom models. And what you're doing there, if they're like well-known, like SSI implementations, etc., we should already have them. If some of you would be contributing, we will have them perhaps, but you would specify those explicitly. You would give, and this might usually not be an optimized version of it, but rather just something that has the same semantics, but you would write it in C. It doesn't matter, right? All you want from that is that CVMC can check the behavior and make sure that it works. And it doesn't have to be implemented efficiently. In point of fact, sometimes you deliberately want to implement those same methods inefficiently, but in a way that's easily understandable and modelable for CVMC. But yeah, those things, whenever we work with sort of platform-specific methods like that, we need to provide models for them.
Thank you.
So we're already in the Q&A phase, so I hope it's not a problem if the clock is blinking aggressively at me that we're at time.
Hello. Okay. I just wonder, is it faster to analyze a compiled binary than the source code, or vice versa? Have you tried that?
I have actually, it's an interesting question. I have no experience with that, but the way I've worked with CVMC and just in my experience, the programs that do analyze quickly versus don't analyze quickly, no, I would not expect that to have much effect. If anything, it might be a detriment. Usually shorter programs, yes, if the compiler removes things, that might help. But the things that tend to kill you in your analysis are things like unbounded loops and other items that just go on forever or have an exorbitant amount of repetitions of the loop body that come to it. And I assume those problems would exist in the compiled or the original version.
So in the case you compiled for memory size, so for binary size, then it might be faster then.
Yes, but for binary size, yes, and assume that code gets deleted, that is actually relevant. Yes, that might have an impact. But in my personal experience, that's not the first place where I would try to optimize things. I would add additional invariants, additional restrictions on the formula to speed things up much before I would consider something like that.
Thank you.
Hello? Yeah. So does it support multi-threading? So like atomics, memory fences, and like memory models and things like that?
Mm-hmm. Yeah, these are fences, for instance, and these kind of tools are supported explicitly. Actually, a former colleague of mine, for instance, was working on that for his DPhil dissertation. So yes, these are always explicitly modeled, and it has a model for concurrency. But usually, depending on what you're trying to do, trying to find race conditions, I will say there's usually dedicated tools like Infer, for instance, has a concurrency backend where you're frequently, concurrency is one of those specific properties that I mentioned before, where you might actually be able to optimize a lot by saying, well, I'm not really interested in what value is being exactly written to this shared variable. I'm interested in, is it actually being written concurrently in a non-thread safe way? And so you might actually be interested in looking at those tools instead. But CVMC, yes, you can do this with CVMC as well.
Okay, thank you.
How confident can we be that these tools themselves don't have any bugs that could lead to incorrect results?
Mm-hmm. It's a fair question, might also be a segue to becoming contributors to these tools. But of course, yes, they're still software tools, right? I mean, as you can imagine, if we write a bug what frequently happens is that you don't model the behavior of the program correctly. That's like one source of issues. When I started in the research group in Oxford, actually, when I started my DPhil back in the days, the first bug I had to fix was actually that, like in C++, dynamic dispatch wasn't modeled correctly, which I thought at the time was a very fundamental feature, But then again, I guess no self-respecting C++ developer uses virtual methods anyway, so I guess it's fine. But yeah, that's something that had to be fixed. Absolutely, that occurs. And I guess the confidence from it is, it's definitely much more confidence by default than you would expect from just testing and fuzzing, of course. And I guess just to make an argument from authority, there are other companies that use these tools. I probably wanted to mention this a bit more, perhaps afterwards, but AWS is using these tools to verify the crypto primitives, etc. So at least you can be assured that there's a lot of people and a lot of I would say developers and companies with a big stake in this, working on this. But yes, absolutely. If somebody fumbles a commit, they might introduce an incorrect mapping to SAT, or they might introduce an incorrect mapping on the language itself from the language to the IR. But that's where most of you will come in, because that's, I think, is the prime source of errors. And it's also one of the front ends that you can work on without special knowledge about static analysis. And it's rather more important that you know and are confident about the semantics, that you're familiar with C++20, you know exactly what this does, etc., what it's supposed to do according to the standard, and that you map that correctly.
Yeah, thanks.
Hi. So
I'm curious about how do you deal with a project that has so many parts, or let's say two are enough, that have different versions of the language. Like one part is 10 years old, another one is 1 year old, and they're from different spectrums.
So if it's absolutely impossible for, again, CVMC acts like a compiler, right? But if you're in a situation where it's for some reason absolutely impossible to specify this to one compiler, and you actually, one will be compiled by one and then the other. CVMC's intermediate representation, you can imagine kind of like a bytecode, exists as a file format as well. So what you can do is you can compile these things using CVMC, and you're just compiling, you're not analyzing. And then you can use these compiled files and pass them into one analysis statement into CVMC.
Oh, very cool. So you also have logic for the linker stage.
Yeah, so that's the symbols just need to be defined somewhere. It's in the symbolic world, it's actually much easier. It will just report conflicts if it's defined multiple times, but yes.
Cool, thanks.
Quick question. So do you have experience using CBMC in the DevOps pipelines and so on? So just have it run before a release, etc. Could you maybe say something about it?
Yeah, absolutely. So I worked for an Oxford-based startup as well, DivBlue, his name, where they were using CVMC also to write tests, for instance, automatically back in the days. I think they've since moved to, like everybody else, to more like machine learning, AI kind of techniques, as is the fashion. But yes, the first pitch was actually to run these tools in CI. It's absolutely possible, again, for reasonable programs, and even for huge, or obviously millions of lines of Java code. That's absolutely feasible. But of course, and that's exactly what this slide is about. That's possible, but that doesn't work out of the box, right? I mean, if you just take a huge program like that in CBMC, you're not specifying any bounds, you're not helping it in any way with like certain preconditions or invariants, etc. It will just, run forever and will not return to you. So that takes maintenance. That also sometimes takes becoming a maintainer of CBMC yourself. But absolutely, there was actually the business case of DivBlue in the day included a CI first pipeline.
All cases, but at least some easy entryway. So it looks like more like a scientific work used with just based on the passion to it, not ready to production, right?
Well, I will say it is definitely, it is used in production, of course, yes, but I think your assumption is absolutely right. When we talk about things that are ready to use without any specification from your end, without any configuration, usually those tools fall more into the abstract interpretation domain again, where it's, no matter what the program is, you probably don't want to have null pointer references in it. No matter what the program is, probably you don't want to have uncaught exceptions reach the top of your main functions. That's where tools like infer come into play, and yes, they're useful. But I think for dedicated scenarios that we said before, again, if you're working on like the typical example is like a nuclear power plant software, I think no, that you would always have to sort of specify what is actually the desired behavior and what are the constraints, just because what is safe and desired behavior for one program might be a bug for another program, right? To a degree, the tool actually can't know that, right? For these more precise analyses, that's where you as a user kind of eventually have to come in and specify and help the tool a little bit.
But can at least it be automatically skipped, or like we can get automatically finished result by skipping those indefinite loops cases,
yes.
something like that?
Oh yes, that is possible in CVMC. CVMC has sort of different modes on how to, for instance, handle these loops, and you can, for instance, tell it for instance, you can tell it be, as I said before, over abstract. So for instance, what you can tell it is, well, assume that this loop can finish after a certain number of iterations, and even though you haven't finished the loop, you assume that the program can escape. And that's a behavior that doesn't exist in your actual program, right? It would have continued, but it will try to find bugs that way still. But you can also tell it to do the opposite. Basically tell it, well, unwind up until a certain loop. And if for some reason there's never a trace in your program that exceeds that loop or that finishes after that, and usually there is, right? You have like something like a list and you can have 1,000 elements and then you continue. But if for some reason this loop always continues up to 10 million, you can tell it just don't care about that, right? Just ignore anything that's later. But of course it will tell you safe, even though the program might not be safe, right? That's the risk that you take by doing something like that.
And it's already possible to do with just one single command line parameter.
It's the -- unwind parameter.
Super.
Yeah.
Thanks.
Hey, if you have any experience of combining LLMs with the static analysis tool, for example, if LLM is capable to generate the preconditions, or if LLM is capable to digest your output and automatically fix the code. Thanks.
Yes, it's interesting. Actually, what I said before is obviously my specialization was actually in program synthesis, where you're using these techniques not to check is an existing program correct, but rather you try to explore every possible mutation, again, using SAT solvers or others of your program to see, is there a mutation of the program that is actually correct, that fixes the bug in the behavior, or just to come up with a program, a sequence of instructions from the very beginning. And that has the problem of being the classical approach to that is even more inefficient than the CVMC-based one. And so ML techniques tend to come in there just sort of as a way of, as a means of efficiently coming up with a good basis, like a good boilerplate that an LLM usually can come up with. And then you would sort of the actual behavior, if the LLM, for instance, gets like one constant wrong or something like that, you would have like program repair. I'm working on the next slide, actually, I have a few references with people, and I'm working on a paper with Christina David, for instance, on that as well, where we try to explore the combination of the two. It's currently an extremely fashionable direction in the field of static analysis. Probably just because whatever has LLM on it sells, and so. But it also does make sense because LLMs are sort of like they're sometimes described as intuition machines, right? They're very good at inductive reasoning, sort of to try and come up with like a basic, for instance, like a very quick. If you tell it to generate a unit test, then it will come up with interesting inputs. It will come up with a boilerplate, etc. But it might get like a constant wrong because it can't actually very well do deductive reasoning, where it decides, well, if this is the input, then, for instance, this should be the output. But that's something that these engines can do very well. And so that's why this combination is very popular currently in the literature.
If I have a code that covers like a lot of ifs and external variables, like a flux, I can actually generate test cases for it, right? Like I can say that, okay, this is variables that can be 0 and 1. Mm-hmm. Please generate all the test cases and like see what will happen. Explore.
Is that question whether CVMC can do that for you? Yeah, that's actually, so CVMC out of the box, there's like a small additional module that has like generating these harnesses, but effectively based on the trace that it generated, saying, oh, this is the input, etc., it will then generate like a simple test for you in C or C++ for that matter. But it's fairly limited because to a degree there was actually the mission of DiffBlue that Daniel Kroening founded, where you would effectively take that to the next level. You would not only create these tests and they would be correct, of course, they would have the right types and inputs, etc. And they would use CVMC to make sure you have 100% coverage. So they would, try to cover every line, and they would use the SAT solver to make sure you find the combinations that will go in there. But then when it comes to these days, they're actually much more focused on doing precisely that, but with more ML influence, because what it turns out, even if you cover every line, you might not have actually interesting inputs. And that's again where like the ML portion of it comes in. So that would be DiffBlue as the company that works on that.
But maybe fuzzing will cover that. Like the next step is the fuzzing. Then, like when you running your program, right, and feeding the binary input that can be actually different. So you mentioned the fuzzing before, right?
Yeah,
and
yeah.
Fuzzing is not a static analysis, this analysis of the already compiled program, right? So do you recommend combining those approaches? Because it sounds like they cover different stories.
Mm-hmm, mm-hmm. No, that's actually a good question. Yeah, maybe again, my biases are showing, right? I'm only talking about static analysis today. This is not to say that you shouldn't use unit tests anymore, that you shouldn't use fuzzing for certain cases. Quite the opposite. There's situations where fuzzing will give you quick answers. Diffblue also uses fuzzing, because for some situations it's absolutely unnecessary. Because, for instance, like you can explore your program, the if sort of conditions will not be as intricate. You will be able to cover 100% of your program or interesting lines with it. But there are situations, I think, especially if you have like these, these high value, high risk scenarios like banking, where people's lives are at stake, where the use cases for static analysis fall in. So I would separate those two. I think I've written, again, I'm sure here everybody is extremely intricate high-level C++ engineers, but for my part, I've written controllers, REST controllers where does it really matter if I have a null pointer exception in there? Probably not, right? So there always will exist code like that, but for the ones where it actually does matter, this is the recommendation that I would give. All right, if there are no more questions, then I want to go towards the conclusion. So as I said before, I wanted to be honest with the guys. Again, it's just be as honest as I can be with folks, but it's obviously, if you take a look at this presentation, you'd think, well, everything is well, right? We have tools like Infer, we have CBMC, let's use them all the time, right? But of course, it's not as simple. As I said before, CBMC, for instance, just to name a few, it has a Java front end that still, I think, only supports Java 8. And there's absolutely no reason why it couldn't support, Java 20, Java 21, right? But the problem is, it's just nobody has gone through the effort of actually writing the mapping from the bytecode to the IR, right? Things that have nothing to do with the static analysis behind it, but just that's probably also why nobody wants to do it. It's of course, it's a lot of work for different languages. And the same is true for CBMC. There exists a fork of CBMC called ESBMC, that has better support for C++, but CBMC, if you use it out of the box, it will just very frequently have problems with some template code, etc. Frequently, you will run into issues with those. And again, that's purely issues on the parser side of things that could be easily solved. And usually what that means, just to share a story, when we started using Mariana Trench at my old company, which is a tool open sourced by Meta, we were in exactly that same situation. Meta only uses, or mostly uses Mariana Trench for Android code, which is a specific flavor of Java. We successfully used it for Java Enterprise code. We made it work, but that meant we had to actually start implementing certain bytecode instructions that were missing, that just never occur in any of the programs that the original authors were interested in, etc. And that is definitely a caveat that I want to give you. There are commercial tools that I didn't mention today, and of course, hopefully, if you have a bit of intuition of what these tools do, that will hopefully help you to select the right commercial tool for you as well. But if you're using these open source tools, frequently you will hit missing language support, you will hit missing features, and that means usually you're in some form of open source collaboration. It can work. It did work for Lacework, where we effectively added support for Enterprise, Java Enterprise to Mariana Trench. But that's something where I want to be transparent, right? With most of these open source tools, my personal opinion is that you're never just going to be using it, you will always be working on this tool as well. And you better account for that. Unless, again, you can always go with Coverity or other professional tools that have very similar techniques like these. And if nothing else, you can take away from this talk that you just be able to tell those techniques apart, know where they're good at, and what their caveats are. Before I close, I just want to give a couple of shout outs. These are the people that I had the privilege of working with as well, but also that if you're interested in any of these topics, these are a few names that you probably should know. Daniel Kroening, currently working at AWS, also still a fellow at University of Oxford. He's the original author of CBMC and JBMC. And when you're interested in static analysis and perusing the research, you'll probably come across his name. For the Infer side, there will be Peter Hearn. He came up with Infer while working at Meta. That was sort of his I think, one of his largest contributions to the company, and is still being used. And then Cristina David and Lucas Cordero. Lucas actually created the ESBMC C++ version, but mostly also interested in proving different properties. He's at the University of Manchester. And Cristina David, since I mentioned program synthesis, I'm still collaborating with her in that field. So if that's what you're interested in, program repair, or automatically coming up with correct programs, again, another name to Google for if you're interested. All right, and that's actually already the end of my talk. So if we have more questions, I guess we can discuss over them over drink and the free beer that I heard so much about. But yeah, beyond that, thank you all for your very interesting questions and contributions.
Yep, thank you for your talk. That's all we have for tonight. Let's enjoy free beer.